Good afternoon. It's an immense pleasure to be here. Thanks to Nicola, Joe, others for invitation. It's the third time we had 25th in L'Aquila, actually in Italy, 25th anniversary, 50th in Princeton, now is 60. Perhaps the cadence should shorten up, so we continue going with these meetings. I've been asked to step in and say something about COBE. Again, great pleasure to be able to try to do that for you. Of course, discovery was mentioned. Just to mention, this was worth half of the Nobel Prize divided between these two gentlemen. And then, after all the romantic time, heroic time described by Bruce and Rashid, there was a serious time to prepare for a space mission. So this is a brief calendarium of preparation for COBE. Started with 74 proposals to NASA, failing, resurrected in 76 by forming a team that, out of 3 proposals that focused on CMB, was supposed to put together a concept for a mission unifying 3 of them on one platform. In 77, that concept emerged. COBE was originally conceptualized to be launched on the space shuttle, comprised of 3 instruments, FIRAS, DERBY, and DMR. Everything was going well, then the shuttle exploded, then there was a delay, enormous effort on redesigning for rocket launch, 50% of weight reduction, for example, things that are shocking in terms of when you see the time scale over which this was accomplished. And as Rashid said, 18 November, 1989, COBE was launched. I particularly like this piece because it shows a footprint from conference in '79 in Copenhagen, where Ray Wise went with John Mather and Tim Kelso. The other 2 gentlemen presented a longer paper on COBE design. Ray wrote just that, and it's a masterclass on project description in concise form. It actually contains everything we still should bear in mind. Why you would go to space in blue, and importantly, that predicting already then that, or expecting there that one of the more serious problems for interpretation of the results and comfortable derivation of results would be what he referred to as astrophysical noise or foreground emission that one would have to deal with. How important it was to have a complement of 3 instruments working together, helping one another in dealing with this problem. This is the COBE science team early on. Out of all of these people, we just have Chuck today in the room. Dave Wilkinson's on the left. You see young John Mather. Kind of shocking to see how young some of these people were when such a magnificent project was conceived. And then eventually, of course, they got the Nobel Prize. And I won't speak much about FIRAS. This was a worldwide sensational presentation of the result. I'll only mention briefly that Berkeley-Nagoya experiment a little earlier purported that there was very significant spectral distortion to the black body, which has spawned enormous trail of theoretical work trying to explain it. Gush and Halpern in Canada built a rocket experiment that was supposed to measure that and did, but briefly after COBE. So the confirmation of this result was very fast through independent instrument. And remarkable thing about that was, of course, that not this curve, but the first one presented to the community was the result of only a few minutes of observation of just opening COBE to the sky and pointing FIRAS and getting the spectrum very clean. Of course, it took much longer to get the anisotropy, and I'll spend most of the time on that. This time they got the full Nobel Prize divided by 2. That's the team, some of it with some replacements, some additions, Al Kogut's on the right, Ray Wise on the left. A few years later, he went back, got his prize for gravity waves. That's how it went. So when COBE was being built, this shows already the redesigned smaller doer. This had liquid helium in it that lasted about, 9 months to support FIRAS and DERBY. the MR was passively cooled, observed for 4 years. That's how it looked, packaged for the rocket. This is the artist drawing on the left of what COBE was supposed to look like if it would have launched on shuttle, and what it in the end looked like is on the right. And that picture we remember very well, so I won't waste time on going on it. Maybe just that, of course, it flies over the terminator, looks away to cold space, sun is at 90 degrees, leading to all sorts of interesting problems with interpretation of possible spurious effects leading to anisotropy. This was the scanning, very effective, low Earth orbit maneuvering to allow to get full sky coverage very effectively for anisotropy experiment, and so on. Also, I won't speak much about Derby. That was a long story. Took many years to contain difficult set of measurements. Even today, people, some in the room, are trying to recompute that and see if something better can be squeezed out of the data. But that was their original press release picture of combination of 3 short wavelength and 3 long wavelength channels to indicate more of a stellar component versus dust component of the galaxy, and marveled at. But I'll mostly talk about the MR. So, launched in '89, by the winter of '90, I would say atmosphere was pregnant with expectation. I was in Aspen meeting myself. This was just after, I think, AAS meeting when they make announcements or reports on what was going on. Some pictures like that, I retained the original slides. These were color print transparency, so I scanned them for this presentation. I remember distinctly how Mike Hauser, John Mather came to Aspen and amusingly reported how local newspapers talking about what was presented at AAS meeting used titles like "Satellites, Lack of Data Mystifies Astronomers." A little later, this was a UPI piece after the American Institute of Physics meeting where Dave Wilkinson was talking about COBE. So this is April 1990. I red-colored some of the quotes. Smoothness is disturbing us a lot, and so on. If 1 or 2 years from now the pictures are still looking smooth, we'll be in trouble. So people worried whether what's emerging here is going to confirm Big Bang, as they said, and the linking of theory of structure formation to what CMB should have revealed to us. I didn't comment on it, obviously. I suppose everybody in the room knows this is on the left side the picture, including the first 3 months of the measurement of mostly dipole anisotropy, and after it's removed, starts showing at the bottom at 30 gigahertz galactic emission. But of course, the big splash came in 1992. Discovery was announced. That was at the American Physics Society meeting in Washington. I had the pleasure to be there. Like a groupie, collected some dedications. My prized possession. That picture is still in my pile. And of course, it hit major news outlets everywhere. I flew to Paris 3 days after that meeting, and I've seen that picture on the screen in the plane shown. And what I wanted to revisit here was typically this picture from the discovery time was presented with the commentary that there aren't really real structures here. I mean, most of the stuff in this picture is noise because the instrument is really on the verge of being able to measure anything. So only statistical methods allow to make claims and formulations of categorical nature about what is the signal there, because you shouldn't think about any of those spots seriously. Well, so this is the same picture on the top, and at the bottom is Planck picture, reduced in resolution to the same roughly, and trying to replicate the color scale and everything. So Obviously, they don't look the same, but if you had a little bit of time to ponder that, I would suggest it's not all noise, and as we used to say working on COBE those days, that was pretty good for government work, all right? The full data set looked like this. 3 frequencies, 2 maps per frequency, possibility to combine them, subtract them, measure various effects. A lot of data analysis emerged in methodology, stimulated by COBE. It was a very different world before COBE maps were available with those few thousand elements on them. These are my old 2 slides from 30 years ago, where all of these spectral concepts and representation of data were being put together for my usage. This is returning to astrophysical noise, the picture that was repeated many times by many people, simply to recall that over frequency range where COBE looked 30 to 90 gigahertz, marked in green. For temperature anisotropies, it was staring at foreground emission minimum. And then in the spectral sense or analysis of the maps, so the first batch of papers actually had, well, Chuck led the paper on internal linear combination approach to combination of these maps in order to derive the microwave background anisotropy maps from them. It got a little bit more complicated later on. Some other methods emerged, all of that. In the power spectrum sense, it was interesting that it so happens that foregrounds as we knew them, and we used them in analysis of COBE data, which was Haslam map at 400 megahertz on the low frequency side, and the Derby map from, I guess, 240 microns as a dust tracer, as a template on the high frequency side. We corrected the MR maps using those, and the power spectrum imprint of that in the convention of noise being flat is on the top. That's a 30-year-old plot showing that very steeply decreasing foreground template emission outside of the galactic cut pretty much made foregrounds for temperature, very fortunately for us, only touching the quadrupole itself, and in a very funny way, the galactic emission has a geometry that is sort of opposite to what we thought at the time is on the sky, and the quadrupole was diminished, as inferred from the data, by superposition with galactic emission. Then there was a little bit of a story of developing thread of power spectrum estimation. A big force on that was Ned Wright on the team. When I came to COBE, Ned already had a paper on 2-year data written. He's not a patient man. He pestered us a lot. Why haven't we, other people, done anything about it? We should publish it, publish it, publish it. We waited. I came in with my stuff, and it was an interesting quirk because with Ned's method of estimation, it appeared that that spectrum was extremely steep, very blue, and he insisted on it, and we had to sort this out, and eventually science team made us join horns or something. Ned was very gracious about it. His paper from 94 has a very bizarre abstract. We'll not go over this now because he quoted both his steep result and the correction that came out of this discussion. In 96, we settled the argument. My results were like this. So all these parameter plots, COBE was really sensitive to, in a nice way, to 2, just the slope of the spectrum and amplitude. Tremendously sensitive to amplitude. If you assume the slope close to Zeldovich, we got a 14 sigma measurement on amplitude. Very convincing in the end, but we couldn't really do physics on, say, 3 parameters, but that followed very rapidly when higher angular resolution data came in. So one of the recollection plots on eventually by 96, we estimated spectrum multiple by multiple. The top left plot is measurement from COBE maps with color bands of 95, 99, well, 68 bands around it. The best fitting spectrum blue, slightly tilted, positive. But then when you reverse it and have data in black and models in color, it shows what at that time fitted a little worse than this pure weird spectrum. It was cold dark matter on large scales, but in the matter-dominated universe. Lambda was not yet the flavor of the day. The integrated Sachs-Wolf effect bends the spectrum upward a little bit at low multiples. It fitted data a little less well than the one without lambda, but not in a categorically discriminatable way. So we couldn't actually argue for lambda with COBE. But what we could argue against was what dominated 1980s. That was cold dark matter with a bias of about 2.5 on it, inferred from interpretation of correlations in galaxy distribution in the matter-dominated universe without lambda. Well, this had such a low prediction for signal that when COBE was flying and DMR was integrating, that was one of the contributors to, shall we say, pessimistic expectation of whether COBE would actually measure anything, because people thought that theory was compelling and predicted too little power for COBE to see. Well, it overshot by as much as you can see there.
Chris,
yeah.
5 minutes.
Yeah, I'm almost done. Doing all of this power spectrum analysis, map analysis, we could play with the data a little bit. This was my old plot presented at Morion in '96, where that should be considered the first glimpse, respectively, so of the last scattering surface as the MR revealed it to us. So on the left are 53 and 90 gigahertz maps on their own and their combination on top, and the difference at the bottom, roughly speaking, on scales above 10 degrees on the sky. I would say 3 to 1 significance of these structures. And again, like in the previous plot I showed you, one of the final amusement plots. Planck data on the right side, okay? So I'd say not so bad. Very, very, very nice indeed, actually, for what COBE was. And this was fun. What happened here? And stimulated tremendous impetus. Before COBE even was shut down in end of 95, data released in 96, proposals went in for what became eventually WMAP, Planck. People were thirsty for all the small-scale structure, baryon acoustic oscillations, cold dark matter, all of that. Predictions were amply available in a figurative, sort of cartoonish way. This was a stretch to cover quickly on the sky with CMB measurements what took us about 500 years on the surface of the Earth to get topography as we understand it right now. And that, of course, happened with WMAP, Planck, other experiments, and other people will talk about it. So I'll stop here and thank you.